In this video, we are going to learn all about tangent planes and linear approximations, a natural extension to the work done with tangent lines in single variable calculus. In order to have a discussion about tangent planes, we first need to refresh our memory on the equation of a plane. So the equation of a plane that contains the point x0, y0, z0 with normal vector n being defined as a, b, and c, then the equation of the plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equaling to 0. And remember, it's equal to 0 in this setup because the normal vector is orthogonal to the plane. Given the point and a general point, x, y, and z, we can create a vector on the plane, and those two vectors will be orthogonal to one another. Therefore, their dot product will be equal to 0. If we clean up the equation of the plane, as we often do, ax plus by plus cz equaling to d. D is the constant term we would get by moving the constants to the other side of the equation. We could also get this constant by plugging the given point in to ax plus by plus cz, right? So we'd have two options to find that value. The next piece we'll need is the gradient vector. So the gradient of a function at the point x0, y0, z0 is orthogonal to the level surface of the function through the given point. Right? So this is a result that we defined in the previous video, but we didn't utilize too much. So now we're going to focus more on this piece. The fact that the gradient vector of a function of 3 variables is orthogonal to a level surface at a point. Okay? It's a natural extension. The way we showed it for the 2-dimensional case can easily be extended to the 3-dimensional case, right? Where we said, just to refresh our memory how we argued it, we said the directional derivative at a point, I'm going to go 3-dimensional now, would be 0 if we pick a direction, a unit direction, that keeps us now on the level surface. In the 2-dimensional case, we chose it so it kept us on the level curve, right? And really what that means is we're going to pick a tangential direction, so the direction will be tangential to the level surface, and then that led to saying the dot product of the gradient and the unit vector was equal to 0. And if we have the dot product of two vectors being equal to 0, we can conclude that those two vectors are orthogonal to one another. So we have this vector that keeps us on the level surface. It would be tangent to the surface. And then the gradient vector is normal to the tangent vector, which means it is normal to the surface at the point. Right? A more intuitive sense, if you think about concentric spheres, so imagine you are standing on a sphere of radius 1 centered at the origin, and you want to move to a sphere of radius 2 in the fastest way possible. No matter where you're standing on that sphere, your direction is going to be to jump straight up. Okay? And that would create a vector that's normal to the surface of the sphere where you were standing. Right? So that's an intuitive sense of what the gradient is telling us and why it would be orthogonal. So now combining these two facts, the plane tangent to the level surface of the function f of x, y, z at the point x0, y0, z0 is defined as partial with respect to x at the given point times x minus x0, partial with respect to y at the given point, y minus y0, plus the partial with respect to z at the given point times z minus z0 equals 0. Right? And I wrote this out for you because that's a lot of subscripts, a lot of small details in the notation. Okay, but really what's important is that we see it for ourselves. And the way this is defining it is saying that the normal vector now is the gradient vector at the point x0, y0, z0. Right? So we can use the gradient vector of the function at the given point as the normal vector of the tangent plane. Right? And that's going to make our life a lot easier. Right? So this is that A, that B, that C. We still have the same structure of the equation of a plane. Now, the level surface idea means that if we have a surface in 3 dimensions that we're trying to write the equation of the tangent plane for, we can create a function 1 dimension higher, a 4-dimensional function that has an infinite number of level surfaces, and we're just highlighting one of them that would be the same as the surface that we are starting with. And that allows us then to hone in on this fact that the gradient vector of this function of 3 variables, a 4-dimensional function, is orthogonal at any point to the 3-dimensional surface, a level surface. Okay, so let's put this into application. So find an equation of the plane tangent to 2xyz equals x squared plus y squared minus z squared at the point 2, 1, 1. All right, so first we are starting with an implicitly defined surface. We could not solve this for z if we tried, but it is a 3-dimensional surface. So we're going to go up a dimension and define a function, f of x, y, z. And it doesn't matter which way we move the terms. Let's move the right side to the left. So 2xyz minus x squared minus y squared plus z squared. So now this is a function in 4 dimensions. It has level surfaces that are 3-dimensional. And what we're saying is this surface we're now considering to be the level curve of the function when it's equal to 0. And by doing so, hey, we can kind of change them out. And now that we have this function, we can find its gradient. So that's the partial with respect to x. So 2yz minus 2x. Partial with respect to y. So 2xz minus 2y. And the partial with respect to z, 2xy plus 2z. Now we're going to evaluate the gradient at the point 2, 1, 1. So that's going to be 2 minus 4, so negative 2. And then 4 minus 2 is 2. And 4 plus 2 is 6. So this now gives us a vector that is normal to the surface at the point 2, 1, 1. Well, that's exactly the piece of information we need to write the equation of a plane at the point. We have our point, 2, 1, 1. We have our normal vector, right? So just to highlight, this is now what we're thinking of as the normal vector. So we have negative 2 times x minus 2 plus 2 times y minus 1 plus 6 times z minus 1 equals 0. And if we clean it up, we'd have negative 2x plus 4 plus 2y minus 2 plus 6z minus 6 equals 0. So negative 2x plus 2y plus 6z equals 4. All right, and there's the equation of the tangent plane to the surface that we were given at the point. Now, building off this, another question that we could be asked is to find the normal line to the tangent plane, and that's the line whose direction vector is parallel to the gradient vector that passes through the given point. So essentially we're using the same set of information that we just found, but instead of writing the equation of the tangent plane, now we're writing the equation of the line that is normal to the surface through the given point. So you can see the definition here. In vector form, r of t would be x naught, y naught, z naught. So this is the point plus some scalar t of partial with respect to x, y, and z at the given point, which we should see that is just the gradient of the function at the given point. So we're using the same set of information, and now we're just writing the equation of a line as opposed to a plane. So find the equation for the normal line to that same surface we were just working with through the point 2, 1, 1. Okay, so we had the gradient vector at 2, 1, 1, and that was negative 2, 2, 6. We have a point, and now we're writing the equation of the line, so r of t. And we could write it as one vector. I know above we separated it as the point was one vector and the gradient was one vector. We can write it as a single vector function. So that's going to be 2 minus 2t, 1 plus 2t, 1 plus 6t as the equation of the line normal. We could write this parametrically since they didn't specify, so that would look like x equals 2 minus 2t, y equals 1 plus 2t, z equals 1 plus 6t. I guess you could also write this symmetrically. I'm not sure why you would do that, but you could hypothetically write this in the symmetric form as well. Okay, so find an equation for both the tangent plane and line normal to 2 arctangent of xy plus xz squared equals y squared plus pi over 2 through the point 1, 1, 1. So this is a good opportunity. Pause the video, try this on your own, and see how you do. Okay, so you can see in blue, we've defined the 4-dimensional function whose level surface is the same as the surface we were given, right? We're here working on the level surface that's equal to 0. If we didn't move the pi over 2 over, we could also say that we're focused on the level surface where the function's equal to pi over 2, right? That would be an option as well. Gradient vector, so you can see all our partial derivatives, evaluated at the point 1, 1, 1 gives us 2, negative 1, 2. And then we have our tangent plane and our normal line. So tangent plane is 2x minus y plus 2z equals 3. And the normal line would be 1 plus 2t, 1 minus t, 1 plus 2t. All right, so let's move into our next example. Find all points on the hyperboloid x squared plus y squared minus z squared equals 1, where the tangent plane is parallel to the plane x minus y plus z equals 11. So same ideas, but the application's a bit different. So here we're not looking to write the equation of the tangent plane, we're looking for points on the surface that we're given where the tangent plane is going to be parallel to the plane that they gave us. All right, so if the tangent plane is going to be parallel to this plane, that means that the gradient vector, which we're using as the normal vector, is going to be some scalar of the normal vector of the plane. Okay, so normal vector of the plane, just to get that out of the way, is 1, negative 1, 1. We'll define our 4-dimensional function. So f of x, y, z equals x squared plus y squared minus z squared. And again, for consistency, we'll take the 1 so that we're assuming that this surface is the level surface when this function's equal to 0. If we left it, x squared plus y squared minus z squared, that would be fine. And then we would be considering the level surface where this function's equal to 1. All right, gradient of the function. So that's going to be 2x, 2y, negative 2z. And we don't have a point to evaluate this gradient vector at because that's what we're finding. Okay, but we do know that the gradient vector is going to have to be some scalar of the normal vector. You could use whatever scalar you want. I chose k here, but that is the relationship that's going to have to be true. So that means that 2x has to be k times 1. 2y has to be negative 1, or I'll stay consistent. We'll say k times negative 1. Doesn't really make a difference. K times negative 1. And negative 2z equals k times 1. So we can solve for x, y, and z in terms of k. So x equals k over 2. Y equals negative k over 2. And z equals negative k over 2. Now that we have x, y, and z all in terms of k, we are searching for points on the surface of the hyperboloid. So that means we want to plug back in to the equation of the hyperboloid, now in terms of k, to try to solve for those points. Okay, so that's going to be k over 2 squared plus negative k over 2 squared minus negative k over 2 squared equals 1. So k squared over 4 plus k squared over 4 minus k squared over 4 equals 1. Some of you may have seen simplification earlier, which is fine. So 2 terms simplify. That leaves us with k squared equals 4, k equals plus or minus 2. So then the points that we're looking for occur when k is either positive or negative 2. So if k is positive 2, then our point is 1, negative 1, negative 1. And if k is negative 2, the point would be negative 1, positive 1, positive 1. So those are the 2 points at which we can write the equation of a tangent plane that would be parallel to x minus y plus z. All right, so a nice little application problem of the tangent plane, the gradient vector that we're working with. And that's pretty common with these tangent plane and normal line type questions beyond just basic of asking, can you write the equation of the tangent plane or the equation of the normal line? You're going to see more problem solving type questions where you have to use these ideas to find points or find something else with respect to the surface that you're given. Find an equation of the plane tangent to z equals e to the 2x plus y at the point 1, negative 2. All right, so here, surface is a little different because it's defined explicitly. We have a z equals, but we can approach it the same way. So we can define our function, f of x, y, z. I'm going to move the z over. So e to the 2x plus y minus z. You can go either way. I'm just going to move the z over and stay consistent with that. So the gradient of the function is equal to 2e to the 2x plus y, e to the 2x plus y, and negative 1. So what I want you to notice here is this gradient vector. This was just really the partial with respect to x. No z affected it. Partial with respect to y. And then we had the partial with respect to z being negative 1 since we moved the z over. Now we want to evaluate at the point, but we don't have a z value. So we can easily fix that. Plug in. So z equals e to the 2 minus 2, which is e to the 0, which is 1. So we're evaluating the gradient at 1, negative 2, 1. So still we get e to the 0. So we have 2, 1, negative 1 as our gradient vector. We have our point. So 2 times x minus 1 plus 1 times y plus 2 minus 1 times z minus 1 equals 0. So 2x minus 2 plus y plus 2 minus z plus 1 equals 0. So 2x plus y minus z equals negative 1. And there we have the equation of the tangent plane. Now, this was an explicitly defined function. So we're going to dive a little bit deeper into this case when we have a z equals or explicitly defined function. So in general, for any function of the form z equals f of xy, the equation of the tangent plane at the point x0, y0, z0 can be written as partial with respect to x at the given point x minus x0 plus partial with respect to y at the given point y minus y0 minus z0 equals 0. Notice that the partial with respect to x and y are only evaluated at x0, y0. And that's because for any function in this form, we can define the function to be f of xy minus z. Then the gradient vector is going to be partial with respect to x of xy, partial with respect to y of xy, and negative 1. Right, and that's because f is just a function of x and y, and z is equal to that. So any explicitly defined function, z equals, we can simplify the equation of the tangent plane of the gradient however we want to think about it. Now, why do we focus in on this? Well, if we manipulate a little bit and we solve for the z minus z0 term, so z minus z0 would be equal to then the partial with respect to x at the point x minus x0 plus partial with respect to y at the point y minus y0. And this builds us into our next concept, which is in order to find the linearization or the linear approximation, those terms are interchangeable, of the function at the given point, we solve the above equation for z. So now we're starting to hone in on finding a linear approximation of a function in 3 space. So z equals a function f of xy. We want to create a linear approximation of that function. So if we solve for z, we'd move the z naught term over. Now we're going to replace it with function notation. So that's going to be the function value at x0, y0 plus the partial with respect to x at that given point x minus x naught plus the partial with respect to y at that given point. Scroll down a little bit more. Y minus y naught. And this is our linear approximation. Really what this is, just to give you some context, this is a first degree Taylor series of a function of two variables. Right? We call it a linearization or a linear approximation because our x minus x naught and our y minus y naught terms are both degree 1. We can extend this idea very easily. We won't, so don't get too worried. But we could extend this idea and study Taylor series of functions of two variables, and we would extend this approximation by using the second order partial derivatives and building more terms onto this approximation. Right? But for right now, we're just going to focus on the linear approximation. And this can be used to approximate the function values at points relatively close to the given point. Right? So really what this is saying is the function value is going to be pretty close to the linearization at points near the given point. Now, what does near mean? Really, that means like we draw a small disk of a certain radius. What is that radius? Well, it depends. But the closer we can get to the given point, the more accurate our approximation is going to be. So find the linearization of the function square root of x squared plus y cubed at the point 1, 2, and use it to approximate the function value of 1.03, 1.98. Okay, so our linear approximation is approximately. So first we need to evaluate the function at the point. So f of 1, 2. So that's going to be equal to the square root of 1 plus 8. Square root of 9 is 3. So we have 3 plus partial with respect to x. So I'll just do that underneath. So partial with respect to x is going to be 2x over 2 square root of x squared plus y cubed. So the partial at 1, 2 is equal to 1 over 3. And let's just find the partial with respect to y while we're at it. So that's 3y squared over 2 square root of x squared plus y cubed. I'm doing the chain rule all in this one term as opposed to expanding it out, right? But it wouldn't be any different. So at 1, 2, we'd have 4 times 3, 12. So that gives us a 6 over 3, which is 2. So 1/3 x minus 1 plus 2 times y minus 2. Okay, so here is our linear approximation. And now we're going to use it to approximate the value of the function at 1.03, 1.98. So 1.03, 1.98, that's going to be approximately 3 plus 1/3 times 0.03 plus 2 times negative 0.02. So that's 3 plus 0.01 minus 0.04. So our linearization gives us an approximation of 2.97. And then we can talk about error bounds and things like that. We're not going to dive as deep into that. Okay, but just like with Taylor series and approximations, you can continue this conversation with error bounds and the like. So our last example, now what happens if we have a function of 3 variables and we want to extend the idea of a linearization? So this is what our linearization would look like. So now we use all 3 first order partial derivatives, a partial with respect to x, y, and z, and the structure stays very much the same. Okay, so let's find the partials first this time. So partial with respect to x, so that's y squared z, and then evaluate that at the point 2, negative 1, 3. So we get 3. And you can do this in the form of the gradient vector as well. It doesn't make a difference. You're still finding all of your partials. So 2, negative 1, 3 here is negative 12. Partial with respect to z is xy squared. 2, negative 1, 3. So we get 2. We do need the function value, right? So function at 2, -1, 3, that's going to be 6. So now we can build our linearization. So linearization of this function of 3 variables is the function value plus partial with respect to x, x minus 2, partial with respect to y, y plus 1, partial with respect to z, z minus 3, and now we can use it to find our approximations. So 2.01, -0.99, 2.99 is going to be 6 plus 3 times 0.01 minus 12 times -0.01 plus 2 times -0.01. A lot of decimals going on here. So we have 6 plus 0.03 plus 0.12 minus 0.02. So that's going to be 0.1, so 0.13, so approximately 6.13 as the approximation of the function at 2.01, -0.99, 2.99. So a really nice extension of the work that started with tangent planes that then built into our linear approximations. And again, really what these are, Taylor series. We're not going to dive deeper, but you can definitely expand this conversation to get more accurate approximations using more derivatives. You can also talk about differentials here. We're not going to go into that topic, but differentials also help to kind of talk about the error bound we would get from using these approximations. But for now, focus on our tangent planes, our linear approximations, and how the gradient vector ties into all of that.